Hello all, I'm Harishri and we're going to see the integration and testing of embedded systems. Now, this phase comes right after the design and development of each units that comprise an embedded system, that is, the hardware and the firmware. A hardware is just a board which has all the required components soldered onto it. This can be a commonly seen PCB, which is also referred to as the target board here. A software makes up the logic of how data should flow through these hardware modules and what output should be returned. This is also referred to as the firmware of an embedded system. Why integration? Without the firmware, the hardware is just a dumb device. We cannot do much with some electronic components alone, and just like humans, the system needs to have a brain. So integration of these two modules is done to embed intelligence onto a dumb target board. Testing. The step before integration is testing. There may be errors which are caused by the hardware or the firmware alone. These bugs need to be isolated and eliminated before integration. This process is called unit testing. We come across a term called code memory here. Simply speaking, the memory to which the firmware should be loaded is the code memory. A target board will have an IC or a processor unit. Some processors have sufficient memory for the code. If not, they use external EEPROM or flash memories to accommodate their code. We have 5 approaches for embedding firmware into hardware. In this video, I'll be explaining the first 3. The first one is out-of-circuit programming. Here, we use an external module called a programming device to load the firmware into code memory of our processor. The device generates programming signals, and this is what we need for the actual programming. The device also contains a ZIF socket to lock the processor in place. This processor can also be a chip or an IC, as we have discussed before. Here we discuss the steps of out-of-circuit programming. The first step is to connect your personal computer, PC, with the programming device using a common USB cable. Power up the device. Execute the programming utility on the PC and ensure proper connectivity is established between PC and the programmer. In case of error, turn off the device power and try connecting it again. Unlock the ZIF socket by turning the lock pin. Insert the device to be programmed into the open socket. Lock the ZIF socket so that the chip will stay in place. Select the device name from the list of supported devices. Load the hex file which is to be embedded into the device. Program the device by the program option of the utility program. That is the interface we are using in the PC. Wait till the completion of programming operation. That is till the busy LED of the programmer is off. Ensure successful programming by checking the LED. Unlock the ZIF socket and remove the device from the programmer. Next we come across ISP, in-system programming. Here we don't need an external programming device. Software is embedded without removing the target device from the board. It is also flexible and easy. Should anything go wrong with the integration, we won't have to repeat the 12 steps as seen before. Also, the target device must have ISP support like ISP cable, ISP utility. There is a special power-up mode for ISP operations. Communication in this approach is serial. That is, when one entity communicates, the other does not interfere. For this, two protocols are used, namely Joint Test Action Group and Serial Peripheral Interface. With SPI protocol, communication is performed through two pins, MISO, that is Master In Slave Out, and MOSI, Master Out Slave In. Consider PC is the master, device is the slave. Master sends code as output to device through the master out slave in pin, and the acknowledgement is sent back through the master in slave out pin. Next, we see something common for SPI supported devices. We know that the code memory is the memory in which code exists. To eliminate the use of an external programming device, all the instructions and APIs that translate high-level language to machine code are provided in a boot memory. The boot memory is still a part of the code memory. The final approach I'm going to discuss with you is IAP, or In-Application Programming. This approach of integration is similar to ISP, but here we as users can control some part of the code. There's a status bit which, when set, runs the code in boot memory and which, when reset, runs the user-edited part of code. Some of the previous year university questions from this topic are: 1. Briefly describe out-of-circuit programming in embedded system. 2. Explain the different techniques for embedding the firmware into the target board of an embedded system. We have only seen the first 3 approaches for embedding the firmware. With this, we finished the first 3 approaches of integration. We've also discussed what testing is and the whole purpose of testing before integration. Well, that's all in this video. Thank you for watching.